In this video, we're going to look at parameterized surfaces and surface area. So earlier, we dealt with a parameterized curve. And basically, when we dealt with line integrals, we had curves in a plane or curves in space. And the way we parameterized that was we used a vector valued function. Now, I've written this vector valued function in R2, so we have 2 dimensions, but obviously we've also looked at parameterized curves in R3. We viewed the endpoints of this vector valued function as a curve in space. And if we had a nice function that is where our f of t and our g of t were continuous and one-to-one, then we would get a nice smooth curve in either R2, like I've written here, or R3. So for example, here's a vector valued function in R3 where I've parameterized this t is going from 0 to 4 pi. And we see that we get this nice curve in space when we have one parameterized variable that is t. So that's what we did earlier. We created a vector valued function and hopefully we had smooth continuous curves on the domain and we get this curve in space. So now what we're going to do is we're going to add a dimension. So we're going to add another input. And if we look at the end points of each of these vectors, if we're given 2 inputs, then the vector value function, if it's continuous and one-to-one on the interior of the domain in the UV plane, so the domain here consists of a section of UV plane. Then the set of all terminal points of this vector valued function will form a surface, and we call that surface S. So if we add a dimension, then the set of all endpoints can form a surface instead of forming a curve. We say that the vector value function R, along with its domain, usually capital R, form a parameterization or a parameterization of S. Again, surface there is S. Now, ideally, we want smooth parameterizations. And so for reasons that we'll see later, smooth parameterizations are really nice. If we have 2-dimensional inputs, then the parameterization is smooth if both of the partial derivatives, that is the partial derivative with respect to u and the partial derivative with respect to v, are continuous, and the cross product of the partial derivatives is not the 0 vector on the interior of our domain R. So basically, we want to have nice partial derivatives, and we don't want to have our cross product of the derivatives be the 0 vector. If we get that, then we say the parameterization is smooth. Now, we're not going to worry too much about smooth parameterizations in this section, but it will be important later on when we do integration with our parameterizations. So let's do an example. The goal of most of this section is going to be to start with a surface and create the vector valued function along with the domain that gives us a nice parameterization of the surface. So let's say we have a surface defined by z equals 5x squared plus 2y. And let's try to find a parameterization of that surface over the region in the xy plane bounded by x values from 0 to 2 and y values from -1 to 1. All right, so the surface z equals 5x squared plus 2y looks like this. It's this surface here. And we're not going to do a parameterization of the entire surface because that would be obviously infinite. We're only going to look at the portion of the surface between x values of 0 and 2 and y values of -1 and 1. And when you do that, you just get this purple part of the surface. It's hard to see in this case, but if you zoom out enough, you'll see that the y values go from -1 to 1, and the x values will go from 0 all the way to 2 if you zoom out enough. Again, it takes a minute to get there. So we have this little rectangle in the xy plane. So we're trying to find a parameterization of this purple piece. Okay. All right. Now, this one is a pretty straightforward problem. It's actually nice whenever we have z is equal to a function of x and y. And in this case, it's particularly nice because my x values are bounded by numerical values, and my y values are also bounded with numerical values. So all I have to do in this case is let x be my variable u and y be my variable v. And then notice that since x is between 0 and 2, that means that u is going to be also between 0 and 2. Since my y is between -1 and 1, then v is also going to be between -1 and 1. Now, that's 2 out of the 3 variables now that we've accounted for. What about the third variable? What about z? Well, z is going to be equal to, well, it has to be equal to 5x squared plus 2y. And I can simply substitute in u everywhere I see an x and v everywhere I see a y. So I get 5u squared plus 2v as my z value. Notice that I don't need any other numerical parameterizations. I just need the numerical values for u and v. So how do we set up the parameterization? We set up a vector valued function whose inputs are u and v, and then we have to plug in an x component. Here x is equal to u. Then we plug in a y component. Here y is equal to v. And then we plug in a z component. And z is equal to 5u squared plus 2v. So that vector valued function on this domain, that is u between 0 and 2, v between -1 and 1, that is my parameterization. At least for this surface over the xy, over this region. Now, I know in the previous slides, R was a region in the UV plane. So this is kind of a little bit of a confusing R here. We called R the rectangle, but our region in the UV plane in this case is the same as the region in the XY plane because our bounds are numerical in the XY plane. That won't always be the case. So the algebra of doing a parameterization is just that in this case. Let's do another example. Let's parameterize this surface, that is the surface z equals 5x squared plus 2y, over the region in the xy plane, bounded this time by x from 0 to 2, but y is in between x squared and 2x. Now, when we do a parameterization, we want numerical bounds for our u's and v's. So it's going to be a little bit of an issue. We're going to have to figure out how to parameterize when we don't have necessarily all numerical bounds. Now, I won't draw the surface again, but what I will do is I'll draw out this region that we're looking at on the XY plane, the region that our surface is over. And on the XY plane, going from 0 to 2 in the x value, going from y equals x squared to y equals 2x in the y component, it's this little section. And obviously a portion of the surface will be projected, this little section will be projected onto that portion of our surface. Now, the first thing we have to realize is that when we do bounds on u and v, we want these bounds to be numerical. And for x, that's perfectly fine. X is from 0 to 2, so we can let u be equal to x once again. And then let u go from 0 to 2. However, we want a number bound for our v. We want a numerical bound for our v. So I can't let v, for instance, go from u squared to 2u by letting v be equal to y. I'll have to be a little bit clever about it. So here's what we do. In a case like this, it's often nice to know that our numerical bound will set to be between 0 and 1 for v. And what we want is when we plug in a v of 0, we want to get x squared. So we're going to let y equals x squared plus v times some other stuff. That way, when we plug in v of 0, we get x squared. And when I plug in v of 1, I want to get 2x. Well, the first thing I'll have to do when I plug in v of 1, if I want 2x, I'll have to do that. And I'll also have to get rid of this x squared. So it'll be 2x minus x squared times v. Now, oftentimes I don't write it that way. What I do is I'll write minus v times x squared and then plus v times 2x. That way, when v is 1, it clearly cancels out the x squared and then adds a 2x. So if we let our y be this thing, then we span from y equals x squared all the way up to y equals 2x. Now, this is going to also make our z be more complicated, but that's okay with parameterization. Our z here was equal to 5x squared plus 2y. Well, again, I'll do a u substitution in for x. That's going to be 5 times u squared. But when you take plus 2y, when you substitute out for y, you're going to have this expression. You're going to have x squared minus v times x squared plus v times 2x. I'm going to write 2 times v times x there. I'll multiply that out. And if you wanted to, you could, do a simplification. And so that is what's giving your parameterization. Your parameterization is, again, going to be this vector valued function. The x component is going to be u. That's pretty simple. The y component is going to be x squared minus vx squared plus 2x times v. Again, remember my x was u. So now I can replace all these x's with the letter u. I could have done that earlier. I just didn't. So my y component is going to be u squared minus v times u squared plus 2 times v times u, or u times v. It doesn't matter what order you write those in. And then my z component is going to be 5u squared plus, I'll distribute the 2. That's 2u squared minus 2vu squared plus 4vu. And if you want to combine like terms there, 5u squared plus 2u squared is 7u squared. So that is the parameterization. This vector valued function along with these bounds. That's a parameterization of this surface over this region in the XY plane. So the portion of that surface over the given region in the XY plane. So whenever we have a surface that is the graph of some z equals a function of x and y, where the domain is closed bounded region in the XY plane, and that domain is having x values between numerical values and y values between functions of x's, then we can parameterize our surface that way. We can set up a u as our x. We can set up a function of u and v as our y. And the way we set up that function is we take the initial value minus v times the initial value plus v times the end value. So initial meaning the lowest value of y up to my highest value of y. And if we let my v go from 0 to 1 and do this, then y can be replaced with that function. And then, since z is equal to a function of x and y, I can just replace x with the letter u, replace the y with this expression, and my z component becomes that. So let's do another example of that. In this case, we're going to look at the exact same surface, but this time over the triangle in the XY plane with vertices 0, 0, 2, 6, and 0, 8. All right. Now, in this case, we have a triangle whose vertices are 0, 0, 2, 6, and 0, 8. You'll notice that if you go from 0, 0 to 2, 6, you get the line y equals 3x. Again, x here going from 0 to 2. If we're going from 0, 8 to 2, 6, that's the line y equals negative 1x plus 8. Again, x is going from 0 to 2. And then obviously the y-axis is x equals 0. So that's the other piece of that triangle. So we're going from y equals 3x up to y equals negative 1x plus 8, and x is going from 0 to 2. All right, so let's do this algebraically now. We said x is ranging from 0 to 2, and y is going from y equals 3x up to y equals negative 1x plus 8. I can do that since I have, again, the surface, which is z equals a function of x and y. So I have that type of a surface. So I'm going to do the exact same thing I did last time. I'm going to let u be equal to x. I'm going to let y be equal to Again, I'm going to maybe move a step ahead here. Obviously, since x goes from 0 to 2 and I'm letting u be equal to x or x be equal to u, doesn't matter which side you put which on, we're saying u is going to go from 0 to 2. We're going to do the trick that we did last time. We're going to let v go from 0 to 1. And then when v is 0, we'll want to be at 3x. When v is 1, we'll want to be at negative 1x plus 8. So I'm going to do minus v times 3x, so that when v is 1, the 3x cancels out, and then plus v times negative 1x plus 8. Now at this point, I guess last time I didn't do the u substitution until the very end, but now I'll do the u substitution. 3u minus, this will be 3 times v times u, or 3uv, doesn't matter what order they go. And then when I do a u substitution here, I get negative 1 times u times v, and then plus 8 times v. Simplifying that gives us 3u minus 4uv plus 8v as my value for y. In fact, I'll just delete that. So that's my value for y. And my value for z is what I'm going to get when I plug in u for x, and this 3u minus 4uv plus 8v for y. I'll go ahead and do that right now. Z is going to be equal to 5 times u squared plus 2 times 3u minus 4uv plus 8v. We'll simplify that when I put it into my parameterization. So the vector valued function I want is going to have x component, which is equal to u. It's going to have y component, which is this 3u minus 4uv plus 8v. And it's going to have z component, which is 5u squared plus 6u minus 8uv plus 16v. Again, that's when I multiply that out, distribute that 2, that's what I get. There's no like terms in any of the components now. They're all as simplified as I can make them. And so this vector valued function, along with this domain, that is u between 0 and 2, and v between 0 and 1, that is my parameterization of the surface I was looking at. Now that technique that we saw, the one described here, that works really, really nicely when we have z equals a function of x and y as our surface. You can also, if ever I have a surface where I can solve for x, I get x equals a function of y and z, then I can do a very similar technique. Or if I have a surface which I can go y equals a function of x and z, I can do a similar technique with that as well. So let's look at an example of a surface that doesn't have a z equals a function of x and y available, but will have an x is equal to a function of y and z available. So the surface that we're going to look at is the rectangle in space with corners 0, 0, 0, 0, 3, 0, 0, 3, 4, and 0, 0, 4. You'll notice that in each of these corners, the x value is 0. And that means this is a portion of the plane x equals 0. So you can think of that x equals 0 as being a function where x is a function of y and z. So what I'm saying is that the surface is actually a portion of x equals 0. And if you look at y values are going from 0 up to 3, from 0 up to 3. So this is x equals 0. And our bounds that are given are bounds on essentially y and z. Y is going from 0 to 3. Z is going from 0 to 4. Now this one might be, well, it is fairly simple, but we'll get into another little bit harder example. But again, we're thinking of this x equals 0 as x is equal to some function of y and z. Okay, so we're going to treat it the same way we did our very first example. I'm going to say, well, now that x is equal to a function of y and z, I can let y, since it has numerical bounds, be my u. And then since the z also has numerical bounds, I can let the z be equal to my v. And then if this were a more complicated surface, I could just plug in u and v into the function, or excuse me, yeah, into the function. And here there's nothing to plug in because it's the constant of 0. So what's going to happen, since y is equal to u, y had those numerical bounds, we'd say u is going to go from 0 to 3. Since z is equal to v, we know z and v are going to go from 0 to 4. Now x is this really basic function. X is going to be 0, the constant function of 0. Y is going to be u, and z is going to be v, the x, y, and z components, that is. So this vector valued function, along with these numerical bounds, or in other words, this vector valued function on this domain, gives a parameterization of that rectangle whose corners are 0, 0, 0, 0, 3, 0, 0, 3, 4, and 0, 0, 4. In Desmos, you can actually take a look at what's happening here. So there we go. We have x equals 0 here graphed, that surface graphed in the gray. And if we go at our corners of 0, 0, 0, 0, 3, 0, 0, 0, 4, and 0, 3, 4, we get this purple, kind of hard to see there, that purple rectangle portion of that. And we can actually graph that vector valued, or excuse me, yeah, graph a vector valued function with two variables if we want to in an app like Desmos. So we just get this rectangle that's a portion of the YZ plane, or the plane x equals 0. So there you go. You get a portion, that's that rectangle. Let's take a look at another example. Now, in this case, it's going to be very different from our previous examples, because while no z equals f of xy was available in this case, there was an x equals a function of yz available in this case. And so in this situation, we're going to have a cylindrical surface generated by an ellipse. So here's an ellipse in the YZ plane, and we're going to extend that into 3 dimensions by letting the x values go from 0 to 5. So y squared over 36 plus z squared over 4 is equal to 1. And we're going to let our x range from 0 to 5. Now this surface can't, in one shot, be solved for z or be solved for y, because they're both squared. And if I try to solve for z, I'm going to get a positive and negative square root. If I solve for y, I'd get both a positive and a negative square root. So we're going to treat this one a little bit differently than what we've had before, because it doesn't solve for z and it doesn't solve for y very nicely. So just that we're on the same page, we have this elliptical cylinder here. And as you can see in the YZ plane, it makes this ellipse. And then we extend that ellipse out. We've dealt with cylinders before, along the parallel line, which is the x-axis. So extend that out along the x-axis from x equals 0 to x equals 5. So we get this object here. Now, in this case, it just so happens that this ellipse has a nice parameterization in a two-dimensional sense, whereas we're inputting one variable and we're getting out the ellipse. So we're inputting a single variable and getting out an ellipse. Now, that parameterization relies on the Pythagorean identity for trig functions, that is cosine squared plus sine squared is equal to 1. And obviously, when we go from x of 0 to x is 5, we're going to have to use one of our variables for x. X has numerical bounds from 0 to 5, so I have to use 1. Now, it doesn't matter which variable we use. I could use the u as my x, or I can use the v as my x. But whichever way I do it, the other variable I'm going to use for my parameterization of the ellipse. So let's use x equals u so I can go into the parameterization of my ellipse, okay? Again, we're going to use the fact that cosine squared plus sine squared is equal to 1. And it turns out if I put 6 times cosine of v as my y value, then when I plug it in here, 6 cosine of v divided by 36, let me rephrase that. 6 cosine of v squared divided by 36 is going to give me just cosine squared. If I let my z value be 2 sine of v, when I plug that in, then I get 2 sine of v squared over 4. And that will give me sine squared. So if I let y be 6 cosine of v, I'll type this in. And I let z be 2 sine of v, then that will satisfy this equation here, because this equation becomes cosine of v squared plus sine of v squared is equal to 1, which is our Pythagorean identity. All right, it's a trig identity that comes from the unit circle. So that's what I'm going to let my y be, and that's what I'm going to let my z be in order to have this equation always hold true. Now, if we do that, since we're using trig functions, if I want to go all the way around the ellipse, then I need to go from 0 to 2 pi radians. I need my v to go all the way from 0 to 2 pi. That'll get us all the way around the ellipse. And then letting my u go from 0 to 5 will extend that ellipse out in the x direction the way I want it to. So now we're set. With this parameterization, my x component of the vector valued function is going to be u. My y component is going to be 6 times the cosine of v. And my z component is going to be 2 times the sine of v. Now, I will point out here that I picked 6 cosine of v for the y. If somebody else would have picked 6 times sine v as the y and 2 times cosine of v as the z, we would have gotten the exact same surface. It would have just been, the ellipse would have been traced out a little bit differently. So we would have ended up with the same surface. And that shows you that parameterizations, just like when we were dealing with parameterizing a curve in space, parameterizations of surfaces are not unique. There's lots of different parameterizations of surfaces. But there it is. There is the one that we've created. And if you ever want to check, you can always graph both surfaces in something like Desmos or do it by hand, although by hand's a lot more difficult. But here was our original surface, the one that we looked at earlier that we had in purple. Notice that this parameterization gives you the exact same surface. All right, u 6 cosine v to sine v, u going from 0 to 5, v going from 0 to 2 pi. Let's do one more that's similar to that. Let's look at example 6 here, which is the surface, which is an ellipsoid. So we have x squared over 25 plus y squared over 49 plus z squared over 9 is equal to 1. Now here, this ellipsoid is centered at the origin. It looks like an elliptical shape in every plane, in the xy plane, in the xz plane, and in the yz plane. So it's this elliptical shape. And once again, we're going to use the trick of trying to create cosine squared plus sine squared equals 1. This one is going to be a little bit more difficult because we have 3 variables. So here's the picture of our ellipsoid. Obviously, in this case, while x does have some numerical bounds, x can go from, if you kind of look at this, x can go from -5 to 5. That's not going to be the most efficient way to do this. And the same thing, y has some numerical bounds, z has some numerical bounds. But if we want to do this in an efficient way, parameterize this in an efficient way, we don't want to have just u is equal to x, or u is equal to y, or u is equal to z. So we have this almost spherical, it's not a perfectly round, but it's elliptical figure. And like I said, we're going to utilize the fact that cosine squared plus sine squared is equal to 1. So here's how we do that. What we're going to do is we want this x squared over 25 to end up being like a cosine squared. If I do that, then this whole piece has to end up being something like a sine squared. The way I get these second pieces to combine and give me a sine squared is to introduce a new cosine squared and a new sine squared. So let me explain. We're going to let x be equal to 5 times cosine of u. And that way, when I plug in x into this function, let me just go ahead and do that. I get 5 times cosine of u squared. It's pretty easy to see that when we do that, 5 squared over 25 is going to become a 1. And that first term will be cosine squared of u. Now I want this stuff to become a sine squared of u. So in order to do that, I need y is equal to 7 times sine of u. But I also kind of need z is equal to 3 times sine of u. If I had those, one or the other of those, then we'd be all set. However, they have to combine, and therefore, what I'm going to do is I'm going to add in an extra sine of v and cosine of v. So I'm going to add a cosine of v, or I'm going to multiply times a cosine of v in order to get my y, and then multiply times a sine of v to get my z. So here's what's going to happen. When we plug in 7 times sine of u times cosine of v and square that, 7 squared over 49 will just become a 1. So we'll get sine of u squared times cosine of v squared. And in a similar way, when I plug in 3 sine u sine v into my z, I'm going to get 1 times sine squared of u multiplied times sine squared of v. Now here's what happens. Both of these terms have a common factor of sine squared of u. So I can factor out sine squared of u from both terms. Now I have cosine squared of v plus sine squared of v. That will become a 1. And then 1 times sine squared is just cosine squared plus sine squared, cosine squared of u plus sine squared of u. That is a 1 by the Pythagorean identity. So that's what I'm going to let my vector valued function be. 5 times cosine of u as my x component, 7 times sine of u times cosine of v as my y component, and 3 sine of u sine of v as my z component. If I do that, then I have the right vector valued functions. Now, the domain is a little bit tricky. A lot of times we think, well, since we're doing cosines and sines, we need to go from 0 to 2 pi on both u and v. However, I need one of these to go all the way around and the other one to actually just rotate pi radians. Let me explain that by looking at the picture. So basically, if I let something go all the way around, that makes like an ellipse. Think of drawing a line around this ellipsoid in the XY plane. If I rotated that, or I should say an entire curve rotated around the ellipse in the XY plane, if I started twisting that around, by the time that one of the sides of my curve gets all the way around this ellipse to the other side, that is going to be a pi unit twist or pi radians. So by the time one side hits the other side, I've gone pi radians. And as I twist it this way, the side here, twist around, move it around, I've gone pi radians. So I'll try to visualize this the best I can. I've put my vector valued function in. If we let u go from 0 to 2 pi, that's kind of like going all the way around the ellipsoid here. And if I make my v go from 0 to 0.1, then we just get a low band of the ellipsoid, a small band on the ellipsoid. As you start making your v bigger, let's say we make our v 0.3, then the band gets higher, or 0.5. So as we get v bigger, you can see that we're going around the ellipse. And once we end up at like pi over 2, we've gone halfway around the ellipse. We keep going around and around and around. And by the time you get to 3 point, let's say 1, you get almost all the way around. And by the time you hit pi, you've gone all the way around, and this portion has touched the other side. So going from 0 all the way around to pi, then the portion of that band touches the other side of the ellipsoid. And so we get that nice parameterized surface that we want. So that's the way we can parameterize that ellipsoid. Okay, this is not the only way you can do it, but this is one of the nice ways to do it. Utilizing the fact that cosine squared plus sine squared is equal to 1. But when you do that, when you're using two trig functions, you have to be really careful about the bounds. U here can go from 0 to 2 pi, but V should only go from 0 to pi if I want to trace around that ellipsoid once. If you go from 0 to 2 pi with your V, you'll trace around the ellipsoid twice, so you'll get double whatever the surface is. Now, another type of problem that we can encounter is trying to parameterize each of the bounding surfaces of some object in R3. So let's assume we have a domain in R3 that's bounded by z equals 2y, y equals 4 minus x squared, and z equals 0. Now, this is going to be an object which has multiple surfaces that create it. And we're asked to parameterize each of those bounding surfaces. So let's take a look at a picture to visualize what's going on, and then I'll find a parameterization for each of the bounding surfaces. So basically we get three surfaces in R3, and we're looking at where they all sort of overlap and create a finite bounded space in R3. That's going to be this section right here. So if I were to highlight that, this section in here, whoops, this section right in here, the portion of y equals 4 minus x that is above z equals 0 and under z equals 2y, that portion there. So let me actually try to graph this. We're going to go from, obviously, we go from 0, y value, up to 4 minus x squared, extend that to 3 dimensions, and then look at z values between 0 and 2y. Let's change the color on that so it's easier to see. Okay, so this is the section I'm looking at. So this is my domain here. And you'll notice that this domain, the boundary of this object, has three surfaces. It has this curved portion of 4 minus x squared, this flat portion up here of z equals 2y, and this bottom portion down here of z equals 0, or the xy plane. So it's a piece of the xy plane, a piece of z equals 2y, and a piece of 4 minus x squared as the surfaces that make up the boundary of this three-dimensional object. So let's do the parameterizations for each of those pieces, each of those surfaces. And I'll start with the portion of, well, it really doesn't matter. Let's do the portion of z equals 2y. All right. And then we'll do the second, which is the portion of y equals 4 minus x squared. And then the last will be the portion of z equals 0. Actually, maybe I'll do that second because it's going to be very similar to z equals 2y portion. We might skip around. So if I'm looking at the portion of z equals 2y, well, I want you to notice that the y values on this are going to go from 0 up to 4 minus x squared. So the y value goes from 0 up to 4 minus x squared. Now, why are the y values going from 0 up to 4 minus x squared? Well, because when we looked at that graph, we could see that if you were going from y equals 0 to y equals 4 minus x squared, it's basically that straightforward. So again, the portion here of z equals 2y, that portion, if I look at it in the y direction, we start at y equals 0 and we go up to y equals 4 minus x squared. Now we could have also figured that out by the fact that we could have done that algebraically as well. I'll mention that in just a moment. But before I get to that, I want to say the x values are clearly going from -2 up to +2 when I'm looking down at this surface. So x values are going from -2 to +2. Y values are going from y equals 0 to y equals that curve, 4 minus x squared. So let's write that down. So y value is going to go from 0 to 4 minus x squared. X values are going from -2 to +2. Now I could have figured that out because remember the domain is bounded by z equals 0. So, and we had z equals 2y. So basically, if z is equal to 0 to z is equal to 2y, that means the lower bound had to be y equals 0, and the upper bound is obviously up to 4 minus x squared. And since all of these things need to be positive above 0, then the only way I get a positive value here is when x is between -2 and 2. So algebraically, I could have seen that as well in a fairly straightforward manner. Z equals 0, plug in 0 for there. That means y has to be 0 at the bottom, and then y has to be 4 minus x squared at the top. And then since y is positive, that means x values have to range from -2 to +2. All right, so when we see that, it's pretty obvious what we're going to do. We're going to do something like we did at the very beginning. We're going to let x equals u, and we're going to let y equals, well, the lower part is 0. The upper part is 4 minus x squared. So I could do 0 minus 0v, so that when I plug in a v of 0, I get 0. And when I plug in a v of 1, I get 4 minus x squared. So that's what I'm going to end up doing. I'm going to go from u of -2 to +2, a v of 0 to 1. My x component is going to be u. My y component, now remember, x is equal to u, so I can replace this x with a u. My y component is going to be 4v minus u squared times v. And since z is equal to 2 times y, that's the portion that I'm looking at. Z is equal to 2 times 4v minus u squared v. I'm going to get a z component that is 8v minus 2u squared v. So that's the portion of z equals 2y. Now, if I go down and look at the portion of z equals 0, this is, again, z is equal to a function of x and y. Here, z is equal to a function of x and y. All of this is going to continue to be the same. So if I'm looking at the portion of z equals 0, I know y goes from 0 to 4 minus x squared, x goes from negative 2 to 2. But this time, since we're looking at the portion of z equals 0, z equals a function of x and y just becomes z equals 0. And that's my parameterization. So the x component is going to be u. The y component is going to be 4v minus u squared times v. And then in this case, the z component is 0. Again, we have in both of these portions, z equals 2y, z equals 0. We have the exact same thing for x and y components, and it's just z equals a different surface. So the only thing that needs to change in those two is which surface that I'm using. Am I using the surface z equals 2y or z equals 0? Now the last portion is the portion of y equals 4 minus x squared. In this case, well, we're going to take the portion of that whose z values are between 0 and 2y, so my two surfaces, and because I have to have positive inputs, x values are also going to go from negative 2 to 2. So I'm going to do the standard thing. I'm going to let x be equal to my u. My y now is 4 minus u squared. I get that because it's on the surface. And then my z is going from 0 to 2y. So I'm going to let the value of v go from 0 to 1. When I plug in 0, I should get a 0. And then when I plug in a v value of 1, I should get 2 times y. Now, if you think about that, I just get v times 2y, but recall y was 4 minus u squared. When I multiply that all out, I get z is equal to 8v minus 2 times u squared times v. Again, u is equal to x, so u has bounds from negative 2 to 2. V goes from 0 to 1, and therefore my parameterization is u, comma, 4 minus u squared, comma, 8v minus 2u squared times v. So there you go. Those are three parameterizations of the three portions of that three-dimensional object that we saw in Desmos. So those are the surfaces that create the boundary of that object. Let's do another example like that, where we have to utilize multiple surfaces. In this case, let's create a three-dimensional object which is bounded by the paraboloid z equals 36 minus 9x squared minus 4y squared and z equals 0. So the paraboloid here is going to point down and it's going to intersect the xy plane. And so we want the portion of that paraboloid above the xy plane. And I don't mean just the paraboloid itself. We're talking about D is the interior. So the paraboloid is the bounding surface and the xy plane is the other bounding surface. So here's what our bounding surfaces look like. As you can see, the paraboloid is this purple. It's hard to see because we have to zoom out because it goes all the way up to 36. But it's pointing down. Obviously, it goes down forever, but we want the portion above the z equals 0 or the xy plane. And that's the z equals 0. So what we're looking at is this domain here. Now you'll notice that this domain has the top surface as the paraboloid, but there is another surface here on bottom, which if you zoom in, is just a portion of the XY plane contained inside of an ellipse. Okay, so the portion of the z equals 0 that's inside this ellipse and the paraboloid section. So we're going to find parameterizations for those two surfaces. All right, so I'll start with the portion, the part of that domain, which is the z equals 0 part, the underneath interior of the ellipse. Okay, so the interior of the ellipse there. Now, how do we find which ellipse are we talking about? Well, again, this is where z equals 0 and z equals 36 minus 9x squared minus 4y squared intersect. So we're talking about the ellipse in the xy plane, which is 0 equals 36 minus 9x squared minus 4y squared. And we can rewrite that. We can solve, add 9x squared, add 4y squared to both sides. And then if you wanted to see it in the way we saw a standard version of the ellipse, just divide both sides by 36. If you do 4 divided by 36, you get y over 9. 9 divided by 36, we get 1/4. fourth, and so that's the ellipse we're talking about, okay? So if we want to, we can start thinking of this in the same way we did before. If we wanted to get the boundary of this ellipse, we do x equals 2 cosine of, let's say, u, and y equals 3 times sine of u. That would give us the boundary, but we want the entire interior of that. So we basically want to go from the exterior boundary to all the way to the point 0, 0. So if you think about that, this is the boundary. How do I go and get 0, 0 all the way out to the boundary? Well, essentially, I'm going to put a V in front of here and then use V value from 0 to 1. So we'll start essentially at the origin, at the point 0, 0. And as V starts moving closer and closer to 1, we end up getting ellipses inside of the boundary. So we'll fill out the entire space. And then u, if I want to go all the way around, I have to go from 0 to 2 pi. Now, what's z in this case? Well, z is equal to 0. And so we're good to go there. So now we've filled that portion, that interior portion of the ellipse. 2v times the cosine of u is my x component. 3v times the sine of u is my y component, and my z component is 0. Hopefully that all makes sense. Now, in a similar way, if I'm looking at the portion of this paraboloid, it's consecutive ellipses, just like this was consecutive ellipses, but just at different heights. So let me explain what I mean by that. So here I have the parameterization that I gave for the z equals 0 surface. And I know I spoke about this, but let me kind of write out what's happening. As this v goes, if it's at 0, then we're at the origin. And as this v goes up, we're filling this space. So at each individual v value, we're getting a slice of, or a portion of this surface. And at v equals 1, I get the boundary of the ellipse. So that is how I'm getting the entire surface. I'm getting that entire surface through a bunch of ellipses, all the way from v equals 0 to v equals 1. Well, in another sense, I can get ellipses around to create this paraboloid at each different value of v. You'll notice that we get an ellipse here around the paraboloid. So that's what's going to be my goal. So I'm going to create a series of ellipses, and all of the ellipses, just like the ones on the bottom here, are going to go essentially all the way till we hit that boundary. So from 0, 0, all the way till I hit this boundary ellipse at the bottom. And we're at the 0, 0 right here at the top. Again, hard to see in this case because the paraboloid is so tall. But we get this successive series of ellipses all the way down until we hit the bottom. So the same way we filled the portion of z equals 0, we're going to fill this paraboloid, this elliptical paraboloid, and we're once again going to let x equals 2v times the cosine of u. We're going to let y equals 3v times the sine of u. But now the z is going to be determined by a function of u and v. And so I'm going to get 36 minus 9 times x squared. That is 36 minus 9 times 2v times the cosine of u squared minus 4 times 3v times the sine of u squared. Now we can simplify and we can shorten that up. So 36 minus, if I take 2v and square it, 9 times 4v squared, I'm going to end up with z equals 36 minus 36v squared times cosine of u squared. And in the same way, when I multiply this out, I get a minus 36v squared times sine squared of u. Notice that minus 36v squared can be factored out. If I factor out a negative 36v squared, I get minus 36v squared times cosine squared plus sine squared of u. That cosine squared plus sine squared becomes a 1. And so my z becomes 36 minus 36v squared when simplified. So that's what I'm going to do. 2v times cosine of u is going to be my x component. 3v times sine of u is going to be my y component. And 36 minus 36 times v squared is going to be my z component. Now, once again, we want the full ellipse, so we want u to go from 0 to 2 pi. And we're going to fill the space, so the way I designed v is the same way I designed v up here. V is going from 0 to 1. So this gives me the parameterization for the bottom part of that domain, the bottom surface of that domain. And this gives me the parameterization for the top part of that domain. And again, we use circles, excuse me, not circles, ellipses in both of those. So hopefully these types of parameterizations make sense. You can do them all algebraically. Obviously, I like looking back at the pictures. Hopefully it makes more sense when you see those pictures, but this is all algebraically very doable. So now we've parameterized specific surfaces in R3. We've used a variety of techniques, and now we've parameterized the bounding surfaces of a given domain in R3. That means we have to parameterize more than one thing. We've done that a couple of times. And so let's go on and move on to looking at some uses of these parameterizations. So one of the nice things about parametric surfaces is that we can use this parameterization to find surface area. So let's say we have a parameterization that is smooth of a surface over a region which is closed and bound in the UV plane. Well, the surface area is the integration, again, of this surface area differential with a 1 in front. It turns out if I change my integration from integrating over the surface to integrating over the bounded region R in the UV plane, then the surface area differential, ds, changes into the magnitude of the cross product of R sub u and R sub v times dA. So R sub u, that's the derivative with respect to u. R sub v, that's the derivative with respect to v. So these are the partial derivatives with respect to u and v. We take the magnitude of the cross product of those things and then integrate that over R, and we can find the surface area. And so this gives me a way, this integration here gives me a way to find parametric surface area. Again, that all comes from the fact that my surface area differential ds, when I convert to integrating with respect to u and v, becomes the magnitude of the cross product of the partial derivatives. Partial derivative with respect to u, and partial derivative with respect to v. So let's take an example. Let's try to find the surface area for this surface here. S is going to be the plane z equals x plus 1/2 y over the triangle in the xy plane whose vertices are 0, 0, 0, 4, and 2, 0. Now, the first thing I'm going to do here is find a parameterization of that surface. And before I do that, what I need to do is look at the region in the XY plane that we're over. And we're over this triangle here. So we're going from y equals 0 up to, this would be y equals negative 2x plus 4. And the x values are going from 0 to 2. So when I parameterize that surface, x is going to go from 0 to 2, y is going to go from 0 up to negative 2x plus 4. Again, let's write that down. So x going from 0 up to 2, y going from 0 up to negative 2x plus 4. Now we've done this a number of times. We let x be equal to u, and then y is going to be, we're going to let v go from 0 to 1. U here obviously is going to go from 0 to 2 because that's what x bounds are. V is going to go from 0 to 1. When v is 0, we'll be at 0. When v is 1, we'll be at negative 2x plus 4. And I can, right, not worry about adding 0. Negative 2 times u plus 4. We'll replace the x with the u. And then the z, since the z, the surface we're looking at, is x plus 1/2 y, we get u plus 1/2 times y. Now y is negative 2uv plus 4v. I'll multiply that out in just a moment. So my parameterization is u, comma, negative 2uv plus 4v, comma, u minus 1 times uv plus 2 times v. That's what happens when I multiply all of that in. All right. So now what we're going to do, so that's my parameterization. That's sort of step 1. Okay. Now the surface integral, or excuse me, the surface area comes from the integral where I have to find the cross product of this thing when I take the derivative with respect to u and when I take the derivative with respect to v. So in other words, I need to figure out the magnitude of, I'm going to write this copy, r sub u cross product with r sub v in order to do my integration. So now let's find that cross product. So start out taking the derivative with respect to u. The derivative with respect to u is going to be, well, I'll get a 1, comma, negative 2v, comma, 1 minus v. The derivative with respect to v is going to be, hopefully we know how to take partial derivatives of vector value functions. So I take the derivative of u with respect to v, that's 0. The derivative of negative 2uv with respect to v, that is negative 2u. The derivative of 4v with respect to v is 4. And then if I take the derivative of the z component with respect to v, this becomes 0, this becomes negative u, this becomes 2. So I end up with negative 2u plus 4. No, I'm sorry, negative u plus 2. I apologize. I read the wrong line there. Negative u plus 2. There we go. And now we're going to take the cross product of those two things. Hopefully you remember that the cross product of two vectors we can get by taking the determinant of, I think of it as ijk, 1, negative 2, v, 1 minus v, with 0, negative 2u plus 4 times negative u plus, or excuse me, negative u plus 2 in the third. So I take r of u and I put it in row 2. R sub v, I put it in row 3. Take the determinant of that. I'll use bracket notation here. When I look at the I component, remember we find that by eliminating the column and the row that I is in. And then I take negative 2v times this minus negative 2u plus 4 times 1 minus v. So what that gives me, let's undo that. What that's going to give me is negative 2v times negative u. That is 2uv. Negative 2v times 2 is minus 4v. So that minus, if I take negative 2u plus 4 and multiply by 1 minus v, I get negative 2u plus 2uv plus 4 minus 4v. That is just the first component. The second component I get by eliminating the row and column that j is in, and then taking the negative of 1 times negative u plus 2, and then minus, well, in this case, plus 0 times 1 minus v, so you get 0. And then for the k component, I would do a 1 times negative 2u plus 4 minus 0 times negative 2v. I'm going to simplify this. In the first component, this 2uv minus this 2uv are going to cancel each other out. this minus 4v and minus a negative 4v are going to cancel each other out. And I'll get I will get positive 2u minus 4 in the first component. In the second component, I get u minus 2. And in the third component, I get negative 2u plus 4. So that is the cross product. Now, in order to find surface area, I'm going to do the magnitude of that cross product with a double integration over the region in the UV plane. So we're going to integrate, I'll go V from 0 to 1. So my outside integration is the V. And my inside integration will be the U. So I'll go from 0 to 2 on that. The magnitude of this vector here, remember how to get the magnitude, that's the square root of each of the components squared. So I take 2u minus 4, square it. I take u minus 2, square it. And I take negative 2u plus 4 and square it. I'm going to be integrating with respect to u first and then with respect to v second. Now this looks kind of messy at this point, but it actually simplifies fairly nicely. If I factor out a 2 here, I get 4 because I get factor out a 2 and then square it. I get 4 times u minus 2 quantity squared plus another u minus 2 quantity squared. I can also factor out a negative 2 here, square it, I'll get plus 4 times u minus 2 quantity squared. Notice that when you do that, we get a lot of u minus 2 squareds. In fact, we get 4 plus 1 plus 4. We get 9 copies of u minus 2 squared. And this tells me to take the positive square root of that. So square root of 9 is 3. Square root of u minus 2 squared squared. I have to be a little bit careful about this. If I go 3 times u minus 2, I actually don't get the right answer because notice my u values are all between 0 and 2. So if I want the positive square root, what I needed to do is I needed to switch the order of that to 2 minus u. That way I get positive values when I plug in values between 0 and 2. And again, u minus 2 squared is the exact same thing as 2 minus u squared. Now, that's a very easy thing to integrate by hand if you want. You could also use technology. Basically, you integrate that and you get a 6. And then integrate that from 0 to 1, you still get a 6. So it turns out the surface area of this plane over that triangle is 6 square units, whatever units we'd be dealing with. So that's the surface area in this case. Hopefully all that makes sense. The hardest part is remembering how to do the cross product and then magnitude of the cross product. Again, if you want to use technology at this stage to figure out your integration, then you can do that. I obviously simplified it. This was doable by hand, so I didn't worry too much about it. Let's do another example. In example 10, we're going to do one of the surfaces that I've already done a parameterization for. So let's look at the surface, which is the portion of the cylinder y equals 4 minus x squared from z equals 0 to z equals 2y. If you remember, this was one of the three surfaces we did when we found parameterizations for the bounding regions of a domain. So I'll just use that parameterization that we found back in this example here, back in example 7. And we'll use that to find the surface area of that surface. All right. So previously, what we did is we said, let's let x be equal to u, and therefore x and u were both between -2 and +2. And then we let v in the standard sense go between 0 and 1. So we ended up, oh, excuse me, I don't have this right. Excuse me. Okay, now I have it fixed. I grabbed the wrong piece from the last example, the wrong piece from example 7. This is the portion of y equals 4 minus x squared. So u went from -2 to +2, where x was equal to u. Y, since it is equal to 4 minus x squared always, we go 4 minus u squared in for my y. And z goes from 0 up to 2y. So with a v value of 0, we should get a 0. And with a v value of 1, I should get 2 times y. That, in this case, would be 2 times 4 minus u squared. When I simplify that, I'll get u, comma, 4 minus u squared, comma, that is 8v minus 2 times u squared times v. Now let's take the derivative with respect to u. The x component, taking the derivative of that with respect to u, gives me 1. The y component, when I take the derivative of that with respect to u, I get -2u. And the z component, when I take a derivative with respect to u, I get -4u times v. Now, when I take the derivative with respect to v, the x component becomes 0. The y component also becomes 0. And the z component becomes 8 minus 2u squared. So now I'm going to take the cross product of those two things. Cross products are nice when we have lots of zeros floating around. If I want to do the cross product, then I take I negative 2u negative 4uv in the second row of this matrix, and then 0, 0, 8 minus 2u squared in the third row. So I cancel out the first row and then the first column. Negative 2u times this thing will be negative 16u plus 4u to the third minus 0 times something. Then I'll do the j component, cancel out the column and the row j is in. I will get negative of 1 times 8 minus 2u squared. Oh, I'm sorry. I said 16 and I hit the 18. Apologize on that earlier one. So we get 8 minus 2u squared. Negative of that becomes the j component. And to get the k component, 1 times 0 minus 0 times negative 2u becomes 0. So my cross product worked out. Let's make sure I did this right. Negative 2u times 8. Yeah, 2 times 8 is negative, negative 2 times 8 is negative 16. So I get negative 16u plus 4u to the third. That's as simple as I can make that. Then I get negative 8 plus 2u squared. That's as simple as I can make that. And then I get a 0. Now, again, the bounds, u went from negative 2 to 2, v went from 0 to 1. So when we are integrating this, if I integrate with respect to u first and v second, then I'll integrate it this way. The magnitude of that cross product is going to be negative 16u plus 4u to the third quantity squared plus negative 8 plus 2, plus u squared plus 2u squared quantity squared plus 0 squared. I won't write the 0 squared here. You can, in fact, if you want to, do this by hand. And there's a lot of, as you can see, if you factor out a 2u here, you'll get another copy of this. So if you wanted to, you could do some factoring and simplification and do that. But since we have numerical bounds, I will simply utilize my calculator to do this integration. And when I did this integration, I got about 40.46. So about 40.46 is the surface area of that portion of the cylinder from z equals 0 to z equals 2y. Okay. And if you did it by hand, again, you could do this if you wanted to, but it takes a minute, so I don't think we need to right now. Let's do one more. Let's find the surface area of this surface, S is the portion of the paraboloid over the plane z equals 0. So I went with a different paraboloid here so that we can integrate it a little bit easier, but also so that it doesn't go so high when we look at the graph. So 9 minus x squared minus y squared is equal to z. All right. Now we will still parameterize this in a very similar way that we parameterize the paraboloid in example number 8. So that will still carry over, but we'll do it in a slightly different way in this instance. I guess when I said slightly different way, I just mean with different numerical values. It's the exact same way that we dealt with this before, but with different numerical values. So we're going to let x be equal to 3 times cosine of u. And when I want it to, so on the exterior, the boundary, x would be equal to 3 cosine of u, and y would be equal to 3 sine of u. That's on the boundary. And then if you multiply those by v, then you see that you can get those ellipses going all the way from a single point to the size of the boundary. When I plug those in into this equation where z is equal to 9 minus x squared minus y squared, it should be straightforward that we get 9 minus 9v squared as the value of z. Again, if we're going from the point 0, 0 to the boundary, then v is going from 0 to 1. And then the u value, since we're going the entire ellipse, we're going from u from 0 to 2 pi. So that's my parameterization. U from 0 to 2 pi, v from 0 to 1, x is 3v times cosine of u. Y is 3v times sine of u. And z is 9 minus 9 times v squared. If I take the derivative with respect to u, derivative of cosine of u is negative sine of u. So I get negative 3v times sine of u. Derivative of sine of u is cosine of u. So I get 3v times cosine of u. And the derivative of 9 minus 9v squared with respect to u is 0. Now let's take the derivative with respect to v. Derivative of 3v cosine of u with respect to v. Derivative of v is just 1, so you get 3 times cosine of u. For the y component, you get 3 times sine of u. Again, I'm taking the derivative of my vector valued function with respect to v. And then the last component here is going to be negative 18 times v to the first. Now I do the cross product. So I put in negative 3v times sine of u, 3v times cosine of u, and 0 into row 2. And into row 3, it is 3 cosine of u, 3 times sine of u, and then negative 18v. When I do the components, again, remember to figure out the I. We eliminate the column and the row I is in, and then we take this multiplication minus this multiplication. So that's going to give us 3v times negative 18v. That's negative 54 v squared times cosine of u. When I do the j, I eliminate the row and the column, and then I take this times negative 18v, 0 times 3 cosine of u. I know that's ugly there. And then I negate it. So I'm going to get negative of negative 3 times negative 18. That's eventually going to give me a still negative of negative of negative gives me a negative 54 v squared times sine of u. And then lastly with the k, negative 3v sine u times 3 sine u minus 3 cosine u times 3v cosine u. Notice that that is becoming negative 9v times sine squared of u minus 9v times cosine squared of u. And we can factor out sine squared plus cosine squared and get a negative 9v there. Just gonna do that. So that's my cross product. So if I want to find the surface area, I needed to find that cross product. I'll take the magnitude of that and I'll integrate on my bounds for u and v. U is going to go from 0 to 2 pi. V is going to go from 0 to 1. And then we end up getting negative 54v squared times cosine of u. All of that is quantity squared plus negative 54v squared times sine of u. All of that is quantity squared plus negative 9v. All of that quantity squared. Long mess, but that's okay. That's not terrible. You can simplify this if you want to. That underneath the square root, notice you're going to get a negative 54v squared squared times cosine squared, negative 54v squared squared, times sine squared. That cosine squared plus sine squared is going to add up to 1. And so what you're going to get is you're going to get 54 squared, which is 2,916 times v to the fourth plus 81 times v squared. And you're going to take a integrate with respect to u and then with respect to v. By the way, this is actually, if you integrate with respect to u, this is all just a constant. So you get 2 pi times that. So we get 2 pi times this square root. And I'm going to do something. I'm going to factor out an 81 and a v squared. I'd put that in front. By the way, 81 times, to me, 81 v squared. I'm going to factor that out, but then I'm going to have a square root of 36v squared plus 1 underneath the square root left. So we get 9v here. If you want to factor or pull out 18 pi in the front, you can. And you can actually do this by hand with a straightforward substitution. I am not going to do that. I think I'm just going to, I won't show that. Let me say it this way. So you let a variable, let's say a, be 36v squared plus 1, and then do a straightforward substitution. And you can do all this by hand. When it's all said and done, I did this by hand, and I ended up getting, well, pi times 37 to the 3/2 power. Ooh, that's why. Divided by 6 minus pi divided by 6. All right. So when I did all that by hand, that's what I ended up with. I won't do that on this video because hopefully everybody watching this video can do a straightforward substitution process here and then multiply by 18 pi. So that is the surface area of the paraboloid above the xy plane. Remember, we are finding surface area here, and so that is the surface area in this case. Okay, a number of different ways you can write that, but I'll leave it there. Now, I will say this, you can imagine that in some cases, trying to find a magnitude of this cross product and trying to find parameterizations can get really tricky. And sometimes these cross products become very cumbersome. And in those cases, you might want to use technology to simplify how you do the computing. All right. Obviously, the way I did it, I used a few nice examples for finding the surface area, but again, you may have to utilize some technology if this turns out to be fairly cumbersome. So that's how we do parameterizations of surfaces and how we find surface area. This was a fairly long video, but hopefully um, we all learned how to do those parameterizations of surfaces and find surface areas with those parameterizations.